we're going to use what's called the per nRT equation. It's called the ideal gas law, which stands for pressure volume equals the number of moles times the rate constant times T. At this point, you may want to stop and pause, and you may want to write all this down. But it's real important that pressure be in atmospheres or kPa. Volume needs to be in liters. Of course, moles is moles, and the reason it's in, it's number of moles. These are rate constants, and I will give these to you. You will not have to memorize those. And that's an ugly unit he's got behind him, some very, very ugly unit to him. And then temperature. So I'm going to go to the sample problem. Again, if you need that, go back, pause, whatever you need. I have uploaded the PowerPoint. And we're going to be working this sample problem. It says an engineer pumped 6 grams of carbon monoxide gas into a cylinder that has a capacity of 2,000 centimeters cubed. What is the pressure in kPa of the carbon monoxide inside the cylinder at 25 degrees Celsius? Alright, if you'll look, I've got a mass and I've got a volume. I'm looking for a pressure and a temperature. It doesn't have any second volumes, pressures, etc. So you know that P equals nRT is the formula you're going to use. Hopefully you either pause right now and write this down, or I'm going to a blank page because Alright, so we have PV equals nRT. The pressure is what we were looking for. The volume has to be in liters. It was 2,000 centimeters cubed. A centimeter cubed is the exact same thing as a milliliter. So you've got 2,000 milliliters, which will be 2 liters. I told them they don't have to show going from milliliters to liters, but make sure you do go. Moles is what I've got next in my formula. Well, I don't know moles, but I've got that it is 6 grams of carbon monoxide. So I could convert my grams to moles. And we should be able to do that in our sleep now. 12 plus 16 is 28. And I told them I'd like them to take them out at least 4 decimal places. And so here is our moles of carbon monoxide. Now I can put that up there. I keep leaving that 1 out of there. Alright, it asks for it in kPa, so we're going to choose the 8.314 number. Right now, if you're writing with me, you can close your parentheses. I'm not going to make you put the units on the arm, but I need the units because I want to show you something. So I'm going to put his ugly units. That is nothing more than a unit being ugly as can be. And then we would put our temperature, and our temperature is 298 Kelvin. So I'm going to multiply everything across to the top, or everything's on the top I should say, multiply across and divide by 2, and that will get our answer. What I want to show you is the units. Can you see that mole will cancel with mole, and liter will cancel with liter, and the Kelvin will cancel with the Kelvin, and that's going to leave you the kPa, and you should be getting for this 265 kPa. And there's my answer using P equals nRT. So real easy. Make sure this is in liters. Use the appropriate R. Make sure that's in moles. Make sure that's in Kelvin. Alright, last sample problem. Same thing going to go apply. If you need to pause, pause right now and write this problem down. If not, I'm going to a blank page and going to work it. It says that you have torr. Well, torr you can't use in that, so I'm going to have to convert it. You can convert it to atmospheres, or you could convert it to kilopascals. I honestly like kilopascals better just because it's bigger, and I don't have to deal with a lot of little numbers. This is 100.23 kPa. Excuse me, 100.23 kPa. Our volume was 425 milliliters. It needs to be in liters, 0.425 liters. Moles, I don't know. I'm going to use, since I chose kPa, if you had chosen to do atmospheres, you'd be using the other number. I'm going to use the 8.314. And then my temperature here is 297 Kelvin. So I'm going to multiply this side and divide by those two. Let me get my eraser out here for a second, get that out of the way. But you do need to show converting your pressures. And when I get the mole, I come out with 0.0173. That's your moles of oxygen. The question asks for grams, so you simply bring your moles down. That was supposed to be bringing moles down. That should be 1 mole. And then you end up with 32 grams of oxygen. So this one's kind of working the other way. Find mole first, then go to grams. And so whether or not you leave it in your calculator, if you use this number that's up there, I think you get 554 grams of oxygen. If you left this whole thing in your calculator, which I'm kind of guilty of doing, which doesn't hurt anything, I get 552 grams. So one or the other is really close. This is leaving it in the calculator. This is using that rounded number. And there is pretty much using pp equals nRT. Here's the catch. Keep that in liters. Of course, that has got to be in Kelvin, and then it can be either atmospheres or kPa. You'll use the appropriate R for that.